Okay, Newton's method. Uh, Newton's method is really nifty, I think. So Newton's method and what it's used for. So it's used to approximate roots. Or when some function of x equals 0. So that's whenever your graph is going to cross the x-axis. That's going to be where those roots are. And your first question might be, well, why do I necessarily need to approximate these roots? There's lots of different stuff. There's quadratic formula out there. Even if I had maybe like a polynomial like with an x cubed, that I could generally work through that and find these roots. And the answer to that is those kind of analytic methods work really well for kind of lower order polynomials. But once you get higher, like once you get to ones that are like x to the 10th, or even bigger or even more complex equations, doesn't have to necessarily be a polynomial, then we need a way that we can approximate these roots. And so that way that we do that is with Newton's method. So we have x to the n plus 1 equals x to the n minus f of x to the n over f prime of x to the n. So here you see we have an iterative sequence, and if you remember back to your algebra classes, whenever we have something that starts with this, x to the n plus 1, that we have to pick a starting value. So what you're going to want to do is you're going to have to pick an x1 close to the root. Close to the root. Or wherever, usually the best way to do this is graphically, where you just look at the graph and see kind of estimate where it is. And then the reason why is it doesn't necessarily have to be close, but this is going to more guarantee that you get a good result. So let's take a look at an example. Okay, so let's say we have f of x equals e to the x plus x. All right, well, using Newton's method, I can say that x to the n plus 1, that's going to equal x to the n minus the function, so e to the x plus x divided by the derivative. Well, the function or the derivative of e to the x, just e to the x, derivative of x is just 1. So this is the equation that I'm going to use, and I got to pick a value to start. So I've got to pick an x1. So in order to do that, let's pull up our graph. Here we go. So I'm going to say, e to the x plus x. There we go. It comes right up. So, let's just pick -1. Really maybe -0.6 would be a little bit better, but let's just do -1 for simplicity's sake. Now, when I do these, because I have my equation already down, I like to use Excel because it's really, really great. Computers are super awesome for these kinds of things. So you're going to put your x1 in that box because you've got to supply the first value. Now this one, you're going to use this plus Newton's method to calculate your next iteration. So this is going to equal x sub n minus, then I've got e, you do exp for e to the x plus x divided by e to the x plus 1. All right, and cross your fingers. Woo, we did it. All right, so now all you have to do is take this and drag it down, and you can see that this converges. And let's say, you set your tolerance. So let's say you want your tolerance within 5 decimal places. So 1, 2, 3, 4, 5. So you can see right here, once you hit even the 4th iteration, 5th iteration, you've already converged on something where the changes are so minor that it's, you can use this as your estimation. So I'm going to write this down on our page, even though you can't see it, negative 0.5671 and there we go. We've used Newton's method to find this. Now let's say you pick negative 10. Let's say you want to start at negative 10. Well, if you do that, you can just copy and paste that. And let's see how fast this one converges. So we drag this down. And we see that it takes, really just one more iteration, even if we're fairly far away from it, to hit this. However, you do have to be careful because that's not so the case all the time. Let's take a look at another example. So for this one, let's use f of x equals x times e to the negative x squared. Okay, so our iteration then, x sub n plus 1. All right, so that's just going to equal x sub n minus x e to the negative x squared. All right, so we have the derivative of this. So we're going to have f and g. So f prime is just 1. So we're going to have e to the negative x squared. All right. Plus, okay, then this one we're going to have to use, looks like the chain rule, so that we just have our x times e to the negative x squared times negative 2x. All right, so I can factor this out of both. So I'm going to be left with x sub n minus x e to the negative x squared over e to the negative x squared, and then x times that is going to give me an x squared. So I've got, what would that be, 1 minus 2x squared. All right, so there we go. So this is going to be the equation that I'm going to plug in. So first, let's take a look at what this looks like graphically. So I'm going to come up here and delete. Okay, so x times e to the negative x squared. Okay, so looking at this, you see how I kind of have these little dipsy doodle right there. And here's why you have to pick it close, because remember we're taking derivatives. So we're looking for whenever it's going to cross, whenever it's going to cross this, which looks like it's 0 because it's going to get closer and closer to 0 here, but I don't necessarily think that it's going to cross it. So let's say if I pick a value out here, like let's say if I pick it on the other side of -1, remember I'm dealing with derivatives, so it's going to actually just take me further this way instead of a derivative which is going to take me closer and closer to 0. So that's why you have to pick it close. If you pick out here, it's just the derivatives are going to take you out that way. Or if you pick it here, because it's slanting towards that, it's going to take you closer and closer. So let's take a look at that. And then we come up to Excel, delete. Okay, so let's pick it. Let's say 2. We'll start at 2 for this one. So I'm starting at 2. And then this one's going to be a little bit trickier to input, but I think we can do it. Okay, so that is going to be 2 minus 2 times exponent negative that squared divided by, I'm going to have exponent of negative that squared times 1 minus 2 times that squared. Okay, I think that does it. I might get an error here. Let's see. Oh, yep. Okay, we'll accept that and just kind of hope that it works. So okay, so I do this, and you'll see it keeps growing and growing. 3, 4, 5, and you see how it never really converges on anything. Right? It's just going to keep growing and growing. Where if I go back to my graph, let's pick one like 0.5. Let's start at 0.5, and then if I enter this in, it should converge to 0. So we start here at 0.5, and then we're going to copy this and paste it over here. And oops, negative. All right, well, maybe I made a mistake within. Let's try. Oh, here, I think I see it. So delete. All right, so let's start at. Well, we'll just call it. Okay. And then that. There we go. All right, that's looking better. Okay, sorry, I forgot. All right, so you can see here that if I do it at 0.1, or now it should work at 0.5. Oh, no, 0.5 looks like, I guess 0.5 is going to be, not close enough. So anyway, this is a good illustration to say that it's going to be really helpful for you to pick it close, because if you don't pick it close, then you do run the risk, especially on a complex thing like this where you have the derivatives changing from positive to negative and all that. You do run the risk of it kind of going crazy and not working. So, all right, that should be enough. That should get us going on our way. Remember to use this. Again, really helpful and just a really neat way for us to approximate these roots.